Next, we have Professor Usman Khan. He completed his PhD at Carnegie Mellon and his postdoc at the famous GRASP lab at the University of Pennsylvania. He's a very active member of IEEE, where he held a list of elected and non-elected positions. He has a successful career, both in terms of quantity and quality of publishing. He will be talking to us about distributed AI, optimal algorithms for distributed stochastic non-convex optimization. Welcome, Professor Khan.
So yeah, thanks Bilal for the kind introduction, and thank you for the organizers, Shinkyu, Professor Ferron, to invite me to present our work. So this talk is on distributed algorithms. We have been working on a non-convex stochastic optimization problems for a while, and I will show how this is related to robotics, not explicitly, but implicitly, in the sense that when data is distributed across many nodes, and the nodes are possibly mobile, communicating over resource restrictions, then how do we design these algorithms? What performance properties do we need from them, etc. So before I start, of course, no good work can be done without our students, and I would like to acknowledge my students who have done all of this great work, and also National Science Foundation in US for their support. So a quick overview, learning from data, that's our fundamental basic problem. We have data everywhere. You wanna find different patterns in data, so solve different machine learning, training, classification, etc. problems. We have seen many examples recently. Image classification is standard, but we have seen data being used in political campaigns, advertisements, and more in terms of modern machine learning problems, as in deep learning, etc. And we can do a simple thought experiment that if we want to build a classifier that distinguishes between images of class A, let's say dogs, and images of class B, let's say cats, that exist on all of our phones, then the number of images are so large that pulling all of these images at a center, performing a machine learning algorithm there just requires a lot of computation and communication resources. And when we increase the number of classes, which is to say that images of dogs versus cats versus horses versus cows, then the problem becomes too intractable. And in robotics, for example, in modern IoT systems, these devices are also possibly mobile and could have resource constraints. So distributed algorithms allow us to perform learning from data when the data is distributed without bringing them at a centralized location, while helping us care for, let's say, privacy, proprietary nature of the data set, respecting the resource constraints, etc. So I'm going to give a simple example, a classical example of image classification. So suppose that our goal is to identify two different types of images which are taken by a self-driving car. One is a stop sign and the other is a yield sign. So given the collection of all images, and I'm assuming that in order to train this algorithm, these images are labeled, I have all the stop signs that are marked as a star in the left figure, and all the yield signs that are marked as a triangle. So given all these images and their labels, I would like to learn a classifier X that is able to predict these labels. So for instance, if I look at the red classifier X, then it makes some predictions of the labels, but it misclassifies 6 points. So it has not misclassified 3 stars and 3 triangles, because the decision would be that if you live above the classifier, you are a star. If you live below, you are a triangle. And if I consider another classifier, let's say green, it misclassifies all the red points, but it also misclassifies another green point. So I can come up with a strategy. I can say that I want to pick a classifier that minimizes this misclassification across all possible classifiers. So this is what I wrote in math here. So basically, given all data, which are my theta j's, I would predict a class. I would have a classifier X that predicts the label Y hat, and I then compare it with the true label Y, and I want to pick a classifier X that minimizes this loss across all data points. So these problems are important, and they kind of fit in the bigger realm of minimizing or optimization problems. Given a different predictor, for example, I showed you a linear classifier, but if I have a fancy nonlinear classifier or neural network, then this Y hat, which is my prediction, will have a different mathematical form and different loss functions. So I could have a mean squared loss, an absolute error loss, a 0-1 loss, a hinge loss, would give me a different functional form, F. And when I think about minimizing problems, I think about minimizing problems that have different functional forms. So we have seen minimizing quadratic functions a lot. For example, in typical signal estimation problems for linear systems, we want to minimize mean squared errors. Linear regression is the same. In optimal control for LTI systems, we have linear quadratic regulators. We can slightly relax this from quadratic to what we call strongly convex functions. And there the examples are logistic regression with a strongly convex regularizer, or plain convex functions where the functions are just convex. And then we can further relax to non-convex problems where the examples are neural networks, modern reinforcement learning, blind sensing, etc. And in this talk, my goal is to search for a point that minimize these functions X, but you can imagine that under different function classes, the minimizer that I achieve X star will have different properties. And in this talk, I'm only going to focus on first order methods. So that means that I'm only allowed to take first derivative or gradients of these functions F. And in a few slides, I'll go to the problem formulation where the data is distributed, and we would like to learn the classifier X star or the minimum of these functions when these functions are distributed over a network of nodes. So some preliminaries, what I said about quadratic, strongly convex, and non-convex functions, I'll just give you a little more detail to get a sense of the results that I'll show in a bit. So we call a function L smooth. L smooth means that its gradients are Lipschitz continuous. And basically, in plain English, what it means is that the function is differentiable, so nice and smooth, but it cannot grow faster than a quadratic. So it's always bounded above by a quadratic, as I show in the bottom figure here. It's not necessarily convex, so it has multiple minima, maxima, whatever, but it's always the growth is upper bounded by a quadratic, which is controlled by this positive constant L. So in this talk, I'll always assume L smooth functions. The next class of functions that I'll consider are a slightly smaller, not slightly, but a smaller class from general non-convex functions. And these are the functions that we call to satisfy Polyak-Ryashevich condition. And basically the idea here is that a function could be non-convex, but every stationary point is a global minimum. So we rule out the possibility of having a local maxima or a local minima or a saddle point, but the function is not necessarily convex. So this is an example where I showed you, and in math, this is the equation, but not needed really for this talk. And strong convexity, of course, is a special case of this PL condition. And then our friends, convex functions and strongly convex functions, where a function is convex if it lives above all its tangents, and a function is mu strongly convex if it has a quadratic lower bound. So strong convexity, in a way, guarantees that a function cannot have a flat line at the bottom, which means that it'll have because it's bounded below by a quadratic, the quadratic is controlled by a positive constant mu. And that guarantees that the function has a unique minimizer. So there is only one point that minimizes this function. And you can see that mu strongly convex functions generalizes the class of quadratic functions. And for all of these, we of course always assume in this talk at least L smooth, which means that for strong convexity, we have a quadratic lower bound controlled by mu and a quadratic upper bound controlled by L. And the ratio between L and mu is what we call condition number for strongly convex functions. And it's a constant that is often appears in the analysis and kind of drives the complexity results or the rates of these these algorithms. So this is a kind of a picture that represents the relationship between these function classes. So restricting to all L smooth functions, I have functions that satisfy PL conditions as a subset, convex functions as a subset, and strong convexity kind of a subset, the smallest class here. And my goal is that for all these function classes, I want to search for a point X star where the gradient is 0. And the idea, of course, is that if you look at any of these functions, at these triangles, the gradient will be 0. So if I pick a point X star, if I find a point X star when the function is not convex, I don't know if I pick the global minimum or the local minimum. It could even be a saddle point when we have vector valued functions. So that's why when we design algorithms, we have different properties of these stationary points that we want to consider. So as I said, non-convex, the stationary point could be a minimum, maximum, or saddle point. Functions that are general convex or that satisfy the PL condition, the function itself has a global minimum. And for strong convexity, X star, which is the global minimizer, is unique. So X star is also unique. F of X star is also unique for strongly convex function. For PL and convex, X star is not necessarily unique, but the function value is going to be unique. So a classical method to search for these stationary points is gradient descent. And given the audience, I'm assuming all of us know what gradient descent is, but the algorithm basically says that evaluate a function at a point xk and find the gradient there and move in the and reduce x in the direction of the negative gradient. And the new point xk plus 1 will, the value of the function at the new point xk plus 1 will not be more than the value of the function at f. So it is kind of decreasing, depends upon what type of function classes we are considering. The decrease is strict or not strict, etc. And here is something, so for gradient descent, when I look at these function classes, convergence rates for gradient descent, we can describe by, for non-convex function classes, the metric that we are interested in is the norm of the gradient at the point xk. So if xk is the iterative gradient descent, then the norm of the function of the gradient of the function at xk goes to 0 as gradient descent goes asymptotically at the rate of 1 over square root of k. And important thing is that this is the metric that we consider when we are dealing with non-convex functions. When we are dealing with convex functions, the metric we consider is the function value at xk minus the optimal, the minimum function value f of x star, and the rate is 1 over k. And for strongly convex or PL condition functions, we can show that gradient descent gives us the minimum value of the function at an exponential rate, which is also in optimization world we call linear convergence, because when I plot optimization exponential convergence on the log scale, it looks like a straight line. And the reason I am showing you these different functions and these different metrics is because later on when I develop algorithms and show you some results, I'll go back to these notions. So how to extend gradient descent when the data is distributed? So we can do consider a very simple example. So think of linear regression. I have 8 and 10, 18 points here. If I fit a line, when all of these points are considered collectively, then I'll get the black line. But when the data is distributed among multiple nodes, in this case, 4 different type of nodes, this magenta, blue, orange, and green, then you can see that every node, based upon its own data, may have a very different sense of the linear regression. So green and orange nodes would think that the trend is upwards. Magenta and blue nodes think that the trend is downwards, but none of them are anywhere close to the optimal black line. So, and that is the reason that if we cannot pool the data at a central location, we would like to do something smarter than just the gradient descent implemented at each node. And the problems that gradient descent face, of course, is that no two nodes agree on a solution in general, unless they have identical data sets. And the solution will not be optimal at any node unless that node has all the data. And when I go from local gradient descent implemented on local data sets to distributed, what I would require is agreement. Everybody agrees, and everybody agrees on a local on the optimal solution. So this is the problem formulation for distributed optimization. I have a function capf that I want to minimize, and this function is distributed over a network of nodes, and it's given explicitly as a sum of local cost functions. So every node in the network has one cost function f1. In the previous scenario, f1 would be the loss function associated to, for example, the magenta data set, which is 4 points, and f2 could be the blue data set, etc. And then it goes over the entire network. And I want to minimize the loss across the sum of all functions, which is basically the entire data set. Each function is private to node I, which means that they are not allowed to share their data. For now, I'm assuming L smooth and mu strongly convex functions. So each function is, think of that as a quadratic, and nodes communicate over a network, which is a connected graph. This function f, because this is a smooth and strongly convex problem, has a unique global minimizer x star, where the gradient is going to be 0 for the cap f function. So this is a celebrated, very well-known algorithm, which is mix and descent. So what mix and descent does that, instead of doing local gradient descent, right? So if this xkr were to be xki and there is no sum here, then this is local gradient descent. So what mix and descent does is that instead of taking a descent in the direction of the local xki, it will first mix these local xkis with its neighbors. So think about the magenta node 1. It receives xk2 and xk4 from its neighbors. It has its own past xk1, which is the local iterates of the gradient descent. And then communication happens. Everybody sends their estimates to node 1. Node 1 takes an average and then takes the descent direction. So what is the weights have certain property here that they should sum to 1, both in the row and column sense if I write them in a weight matrix, so which means incoming weights and outgoing weights. And what we can show is that what was shown is that DGD converges linearly, so exponentially on the log scale to a steady state error. So it does not go linearly to converge. It converges, the error goes to 0, but it converges up to a steady state error. We can show converges exactly with a decaying step size, but then the rate is slower. So this is how it looks like. So if I plot gradient descent for smooth and strongly convex function, gradient descent gives me a linear convergence rate, but distributed gradient descent is linear and then just settles to a steady state error. And the question we could ask is that why distributed gradient descent does not converge linearly, and what can we do for this to achieve this? So this is the first main point of this talk, where I will show you a method that we call gradient tracking, which enables linear convergence in distributed gradient descent. So again, our problem is to minimize the sum cost when each function fi is distributed over a network of nodes. And I want to find a point x star that such that the gradient of the sum cost at x star is 0. So remember that the gradient at each local cost fi is not necessarily 0, but the sum is 0. So what happens in distributed gradient descent is that assume that on the right side of distributed gradient descent, if I know x star, if every node knows x star, which is the stationary point, then because the weights sum to 1, I get x star here. But the value of the gradient at a local cost fi at x star is not necessarily 0, right? Only the sum is 0. So the right side does not lead to x star. So what I'm trying to say mathematically is that x star is not a fixed point of distributed gradient descent, which means that even if everybody starts with x star, the next iteration they'll lose x star. And this is of course because that x star is not a local minimizer, but a global minimizer. And we call this local versus global dissimilarity bias, which basically means that if this local f cost gradient of fi is replaced by the sum gradient of fi, then I'll remove this problem. So that is the local versus global. So you can see that the bigger the difference between the local fi and the sum fi, the bigger this error is potentially could be. And the fix that we could do is that we could replace each local fi. Of course, ideally you want to replace it with the sum, but nobody knows the entire sum because the data is private. So we replace it with another auxiliary variable y, and y estimates the global gradient f, the cap f. Okay, and this is how the algorithm looks like. So instead of DGD, where the descent direction is the local gradient, which I've shown as red in the second line. I have the descent direction now as y, where the dynamics of y are given by the second equation. Okay, so this y now, with the help of the second equation, tracks the global gradient. And this algorithm we can show converges linearly to the stationary point with the help of gradient tracking of both directed and undirected graphs. So directed graph would be a graph where if node I sends information to node J, then node J does not necessarily send the information back. This is kind of meaningful in the context of robotic networks or Internet of Things type systems, because one device, if it's connected to power, may be able to communicate to faraway nodes, devices or robots, but the robots or devices that are in the field, not connected to power but are battery operated, may not be able to communicate back. And this is just a summary over smooth and strongly convex functions. These algorithms have been well studied over the past few years. I have highlighted a few things at the red, which could be relevant to mobile robotic networks. For example, for instance, we have results when the graph among the nodes is not necessarily connected at every time step, but it's connected in the mean. We have results when these could be random graphs, time varying, but under certain regularity conditions, these algorithms still converge linearly. And we have results where communication could be asynchronous, there could be delays, there could be latency, there could be packet drops, but these algorithms still converge exponentially. Of course, the slope will not be as sharp. Something on condition number dependence. So gradient descent, remember that for smooth and strongly convex function, I had this constant kappa. And the condition number dependence for the algorithm I showed you is kappa 5/4 for undirected graphs and kappa square over directed graphs. You can see we are taking a hit in terms of kappa, and this is where these distributed algorithms can be improved. For a certain different type of class of algorithms, these constants have been improved. We can also add acceleration or momentum by using heavy ball or Nesterov momentum, but for both of these acceleration momentum algorithms, convergence is not proved analytically, but we can, for directed graphs, and we can only show, observe it numerically. And this is how the convergence looks like. So distributed gradient descent converges with a steady state error. This is the magenta line. And then after adding gradient tracking in what I described as the AB algorithm, I recovered linear convergence, which is this blue dashed line. And if I add momentum to it, I get ABM, which is much faster, right? That's the blue one, it's still distributed. And the benchmarks are these black and red lines, which is heavy ball momentum added to the centralized gradient descent, and black is the centralized gradient descent. So what happens when the gradients are imperfect? So this is what the talk is about, stochastic problems. So when the gradients are imperfect, we lose everything in a way. So assume that instead of using the full gradient, wherever I use gradient plus noise. The variance of that noise is nu square. Then the nice convergence that I have on the left figure for centralized gradient descent or for distributed gradient descent with gradient tracking or without gradient tracking, we lose pretty much everything. You can still see that these algorithms converge linearly, but now they converge to a steady state error, the size of which we actually explicitly know. So for distributed stochastic gradient descent, which is this purple curve without noise, when I add noise, I have this purple curve here. The error, the difference between the iterate at node I and the truth x star converges linearly to an error ball. So it converges, the point will converge to a point around x star such that the radius of that error ball, so ignore the equation, but just focus on the three red symbols, depends on nu square, which is the stochastic variance of the stochastic gradient, and eta. So eta is something which quantifies that local versus global dissimilarity bias. And in the magenta algorithm, I don't have gradient tracking. And gradient tracking eliminates this bias. So for example, the blue algorithm here on the left does not have any noise. So nu square is 0. And because I'm doing gradient tracking, the eta is also 0. So for distributed gradient descent with gradient tracking, the AB algorithm, residual decays linearly to an error ball of size 0. So it basically converges to x star exponentially. So in stochastic problems, our goal now is to study the convergence rate of distributed gradient descent type methods for non-convex problems or other function classes or that I showed earlier. And so this is the problem formulation. So I want to minimize a function that is decomposed over a network of nodes. We have two measurement models, and I'll briefly consider both of them. One model is online streaming, which means that at every time step, an oracle gives me a gradient plus noise, let's say, or a gradient with certain statistical estimate of the gradient with certain statistical properties. And another is batch data measurement model, where every node has a collection of images or a collection of data points that are stored in its memory, and they are just probably sampling from that collection, but no new data is revealed at every time instant. And they communicate over a strongly connected graph. So as I described, gradient tracking eliminates the local versus global dissimilarity bias, but the variance remains. And we want to quantify the effect of this variance for different function classes. And we want to provide guarantees to the convergence of these distributed algorithms. So smooth non-convex problem. So this is how the algorithm will look like now. It's very similar to what I had before. The bottom X equation is mixing of the neighboring estimates of the truth, minus a step in the direction of yk, where remember yk was the estimate of the global gradient. But now in the yk equation, I don't have the global gradient, but I have an estimate of the global gradient g. So g is an unbiased estimate of the true gradient, and g has bounded variance. So these are the two assumptions that I have. These assumptions can be relaxed, but I'm going to focus on these for the sake of simplicity. What happens when, what is the function of this algorithm when we have general non-convex functions? Well, this is a bit too much to parse, but basically what I'm saying here is that the norm of the, so remember, so this is the sum over k. So this is basically I'm summing over all k, the norm of the gradient square, right? And this is upper bounded by basically a constant. So if k goes to infinity, you see the first term is 0, the last term is 0, and this is a constant, right? So if the sum of infinite numbers is upper bounded by a constant, then it means that those infinite numbers should go to 0. So that's basically the idea, which means that these xki's, in the mean squared sense, converge to a stationary point. You can see that in my upper bound, there is no eta, so there is no dependence on the global versus local similarity, dissimilarity, but the new square terms are there. So because we had noise, this result is non-asymptotic. We can guarantee a few two properties of linear speedup versus network independence, which basically means that this algorithm is n times faster than its centralized counterpart, because of course there is data parallelization and n times more nodes than a center. And we can show that this algorithm is independent of the network after a finite number of iterations. So this is an important property, because what we are saying is that a distributed algorithm, after a finite number of iterations, start behaving as the centralized algorithm. Next, to non-convex functions that satisfy PL conditions. So here quickly I'll show you that converges linearly, that up to an error ball, and we can zoom into these results if there are questions. And remember that strongly convex functions are a special case of this non-convex functions that satisfy PL conditions. So this result applies to strongly convex problems. And here we can show that the full gradient complexity is kappa to the 5 over 4. That's what I earlier referred to quickly, briefly. And it improves on the best known results on these function classes. We can kill the variance by adding a decaying step size, but and show convergence for both mean squared and almost sure sense. This is what I'm showing in the next slide, but I'm gonna ignore this and we can talk later. But basically the first equation here means that I is a node. So the gradient descent estimate at node I, gradient descent estimate at node J, converges almost surely to an agreement. So they're both equal, their difference is 0. And the xki is also a stationary point in a almost sure sense. The next framework that I described, measurement framework, was this batch data problems, where every node in the network has a collection of images. So think of collection of, one class of images, elephant, stored on my phone, another class of images stored on another phone. Some at some places we could only have one class of images, right? At some other places we could have a small data set but across many different classes. So you can see that if node 1 were to build a classifier that distinguishes between these 6 or 7 class types of images, then node 1 has never seen an example other than an elephant, and node 3 has never seen an example other than a lion. So they would never be able to learn a classifier. So that's why collaboration is necessary. The local cost function now, fi, is the sum over all images, right? So each node, fi, now is further decomposed. The cost is decomposed over every image in this that exists on this node, and there are a total of m sub I data samples. And you can imagine that if I have 1 million images, then computing a gradient of a function that is a sum across all of these images will take me a very long time. So typically what happens is that gradient descent is implemented using distributed gradient descent. But instead of sampling or using the entire data, I pick an image randomly from this data set, and I just run gradient descent on that image. So tau here, so remember J goes from 1 through mi, so mi could be a million, but tau is just a random sample or random number index that I generate between 1 through mi. So I just pick one image and apply in my gradient descent. So every time I sample a new image and then apply. So as long as my sampling is done in a meaningful way, then this algorithm converges. But because sampling incurs noise and incurs a variance, this algorithm will converge to a steady state error. It could be linear if the functions are smooth and strongly convex, but at other rates when they are not necessarily strongly convex. So something that we did in our group is this notion of is this GTVR framework, where in addition to gradient tracking that I showed before, I'll add variance reduction. So what variance reduction does is that, remember that every time we are sampling from our batch, but we use that sample to estimate the batch gradient, my local batch. So I have 100 images, I'll sample one, but then I'll try to estimate the gradient across all 100 images. And this was done in centralized algorithms in about 2011, 2012 with these different type of variance reduction methods. So we use these variance reduction methods, combine them with gradient tracking, and develop and analyze the convergence properties of these methods. So one such algorithm is this Saga algorithm. What Saga does for variance reduction is that at node I have a memory bank in which I have the gradient computed at every sample point or at every image in my data set, right? And then I'll sum those, right? And I'll update my local xi, which is my local iterate. But at the next iterate, I'm not going to compute every gradient, but I'll just sample one gradient and reevaluate the gradient at the new iterate xi. And this is how the process goes. And of course, because this is distributed, there is some network effect mixing going on. You can see that what this algorithm requires is a table of the gradient at every node. So this algorithm requires a lot of storage. And what we can show is that this algorithm has the best performance to the best of our result for non-convex problems in a certain regime that we call IoT regime. And I'll try to say something more in a bit. And it has linear convergence, converges through the global minimum for smooth and strongly convex functions. We can show it in a both, almost sure or mean squared sense. The other algorithm that is quite popular is this GT-SARA architecture. What this algorithm does is that it doesn't require storage as the Saga version, but it requires periodic computations of full gradients. So at node I, I'll start at some iterate, let's say xt. I'll compute the full gradient, which is across all images, right? And then I sample one image, have the next iterate, then I sample another next iterate, sample another next iterate. But after t iterations, I'll recompute the entire gradient. So this, you can see that this is happening parallel at multiple nodes. So node I, or one robot is doing that, another robot is doing that. But what happens is that if one robot or 10 data points, then this gradient computation will be pretty quick. But if another robot has 1 million images, then this gradient computation will periodically take a long time. So you can see that the algorithm cannot proceed because the network has to mix at the time scale t+1. So there is a synchronization issue. Every robot could kind of have to wait for the entire network to finish their local gradient computations and then proceed. It turns out that these two different algorithms, this GT, gradient tracking combined with SARA, gradient tracking combined with Saga, they are optimal in different regimes. And I'll skip this. We can show that for non-convex problems, smooth non-convex problems, the SARA algorithm converges almost surely to a stationary point in both almost sure and mean squared sense. We have also, so the gradient computation complexity is, so this is a bit heavy, but I'll move to the next slide and try to explain the result. So what we have shown that if we want to minimize a sum of n times m smooth non-convex functions, so remember that there are n nodes in the network and every node in the network has little m functions. So I want to minimize the sum, and this is the bash data scenario. So I'm trying to minimize the sum of n times m smooth non-convex functions. And for this problem class, the best that a first order algorithm could do in a stochastic first order algorithm, the algorithmic lower bound is this complexity. So which means that we can achieve an accuracy of epsilon in these many number of iterations. And what we have shown that GT SARA, which is the proposed algorithm that combines gradient tracking with SARA type variance reduction, matches this rate under a certain regime. And this regime basically means that the number of samples, little m, at each node are much larger. So basically, we call this a big data regime. So when the number of samples are large enough, this proposed algorithm matches the algorithmic lower bound until under a slightly stronger assumption, which I can describe if there is interest. Again, the convergence is independent of the variance of the local gradients, right? There is no new square variance here, and there is no bias term here. And we can show network independent performance, which means that in a finite time, there is no effect of the network. And these algorithms are achieve a linear speed up when it comes to in comparison to the centralized algorithms. So I'm trying to be a bit faster in order to get back on time. But this is a demo. So this is a simple demo, but kind of gives a sense of how these algorithms behave. So I have 100 nodes. Every node has one data point, right? That one data point is this blue dot on on all of these right figures. And my goal is that I want to learn the linear regression straight line across all of this data. And you can imagine that since every node has one data point, then every node alone on one data point is unable to fit any line, right? I mean, it would be just one line that goes through this data point. It could be any line. So centralized gradient descent learns the slope and intercept when it's given all these 100 data points. But what distributed gradient descent does is you can see the top right figure, the rightmost figure in the top, and I'll try to run it again. You can see that, so here I have 100 points, but I'm probably plotting 10 or so. Every node starts with some random estimate of the slope and intercept, but as the algorithm proceeds, the blue line, the solid blue line, it's the distributed gradient descent algorithm with gradient tracking. They all agree very fast, right? They agree, and then they converge to the truth, to the true line, to linear regression line. And this convergence is exponential. And if we don't do gradient tracking, then remember this was the magenta algorithm, which converges to a steady state error. So this is the magenta. If you see that there is no agreement, and they of course are not also converging to the optimal. And I can recover agreement if I choose decaying step sizes, which is distributed gradient descent without gradient tracking, but decaying step size with the convergence rate of this black line is very slow. So conclusions. So basically for distributed optimization problems, when the data is distributed over multiple nodes, we have developed these algorithms which add gradient tracking and variance reduction in one form or another to the plain distributed gradient descent algorithms. And we have shown state-of-the-art performance under different function classes. Of interest is the IoT regime. So IoT regime is where we have a large network of nodes. They may not be very well connected. And in that sense, the algorithm that works well is the Saga algorithm. We can show the best performance results to the best of our knowledge. And when we have very well connected networks, what we call big data regime. So think of a data center where we have multiple nodes very well connected together, but every node may have very large data set. We have this other class of algorithm which doesn't require storage, but requires periodic computation of the full gradient that performs better. And for all of these algorithms, there is a parallel story where the networks can be mobile. For example, the graph is not a constant, the interconnections between all the nodes, but they change over time. They could be random, time varying, etc. And in some cases, we can develop results. In some cases, we can see that the algorithms work, but we don't have the analysis. And that is a part of our ongoing work. And before I go, a bit of a advertisement. So we did run a special issue on optimization for data-driven learning and control and proceedings of the IEEE that published last year. So if you are interested in these ideas, distributed learning, distributed control, how optimization is enabling data-driven learning and control, this special issue has, I believe, 12 papers, and it could be very helpful. Thank you.
Thank you very much, Professor Khan, for your talk about optimization, which is a field that gets involved in everything pretty much.